Hi, this is Et250, Lecture 5, Part C. And so in this last part, we're going to introduce this large signal DC analysis for a PNP transistor. Okay, so here's the PNP. Now this one is a little bit trickier than the NPN one, but let's again remind ourselves of the PNP transistor. Pointing in proudly, I have emitter, base collector, emitter attached to the arrow. CE has the positive at the C. BC has the positive at the B, and BE has the positive at the B. And I have all my currents defined as following the directions of the arrow in the symbol. Okay, so let's look at the first one, and that's cutoff. And so like before, if we are to guess cutoff, we would just replace that circuit with an open circuit model, right? And the conditions are kind of reversed from the NPN. So here we got to check, is VBE greater than negative 0.5 and is VBC greater than negative 0.5? And the reason why is because, well, we have a PN, right? P, right? And so this would put it in a reverse bias kind of situation for this one, okay? It might take a minute to get your head wrapped around it, but I think it all makes sense if you follow through. Okay, what about over here? The saturation, very similar. You got the 0.7 volt, you got this 0.2 volts of speed bump, right? So if I can suck current out of the transistor, I can get a large current going from IE to IC. I have this, it's not quite as short, but I have this 0.2 volt bump in the way. And I got to check, is this current positive? Am I actually pulling positive current out here? And the same as before, is beta IB greater than IC greater than 0? Now notice these conditions are exactly the same as the ones before. However, very important thing, very subtle, but notice VCE is actually negative 0.2 volts in this case. And VB is actually negative 0.7 volts in this case by KVL. Okay, so don't get that twisted, all right? All right, so then let's look at the forward active one. And the forward active one here, again, we have a current controlled current source. And that should make sense because this current here, IB and IC are related. And IC is actually this one multiplied by that gain. All right, so not too bad. Same model, same 0.7 here. Again, VBE is negative 0.7, so we can't mess that up. And notice VC is the voltage across that dependent source. Okay, so what do we have to check? We have to check that IB is positive if this is going to be activated. In both these cases, if IB is positive, it turns them on. Now we have to check is VCE less than negative 0.2. So these two here, these two are like the distinguishing conditions to check. If I'm here, if I'm guessing here, I got to make sure I'm not saturation. If I'm guessing this one, I got to check this one to make sure I'm not in forward active. Okay, but otherwise you can just blindly use these tools and follow this procedure, this kind of guess and check procedure to see if you can pick the correct state that this PNP transistor is in. So let's do this example. And so here's an example here where you have a PNP. We can double check. Is it pointing in? Yes, pointing in proudly. This is kind of weird, right? It's drawn weird. It's drawn horizontal. You got this +5, -15, R1, R2. The gate's going down here. It's like, what's going on? You have this V going plus and minus to ground. Super weird. Yes, they give you the resistances, and yes, they tell you that VBE, if you guess this, if it's in these on conditions, it's 0.7. They also give you the beta of 100. But this is a weird setup, right? And the question asks, what's V and I, right? What's V and I? And use the large signal DC analysis, okay? So we know it's PNP. And what I like to do when I see something weird like this, I like to redraw it in a format where it makes a little more sense to me. So I'm going to redraw it vertical, and I'm going to put this +5 volt like this. Okay, so this should look like that tester circuit. I'm going to put the resistor R1 there, the PNP, and I have this resistor R2 there, and then I'm going to put a voltage source oriented negative positive, but give it a value of -15. And I'm going to orient it with respect to ground because that's what this is essentially saying. The node voltage at this point is -15. Okay, then I'm going to tie this to ground because that's what this is saying. And it looks like V here is going from positive this point here, which is the collector, in fact, to this point here, which is now tied to ground. I've also put my voltage labels VBE, VBC, VCE, all my current directions, IE, IB, and IC. And notice I and IC are the same by KCL. And notice by KVL, V is equal to negative VBC, right? You can see that right there. Okay, so now I have this circuit drawn you know, equivalently, but in a more intuitive fashion from my perspective. And again, we have three guesses. We have cutoff, forward active, saturation. And we look here, okay, well, if the node voltage here is around 5, the node voltage here is at -15, the node voltage here is about 0, that tells me that this voltage is somewhere in between these two. And I'm going to, I mean, engineering wise, I guess that that's probably forward active, not cutoff, not saturation. So what I would do is I would take this and I would redraw it with the forward active model, which is this guy right there. Okay, this forward active model here. And so I would, okay, that's a little tricky, but I just got to be careful. It's not too bad. I put in that 0.7 volt, I orient it correctly, and I put in this current controlled current source, but otherwise everything around it is the same. Okay. Now notice I put a voltage polarity over here across the R1 and the R2. Okay, so I know it looks pretty complicated, but if you stick to your Et250 fundamentals, you should be good. Notice I have VCE across the current controlled current source, IC drawn, -15, so everything is consistent. Still KCL, I equals IC, still KVL, V equals -VBC. Okay, now the conditions I need to check is this: IB is greater than 0 and VCE is less than -0.2 volts. Okay, so I still have to check these. And what am I solving for? In this question, I'm being asked what's I, and I is this case, right? This current going down is the same as IC, and what's V? It's this voltage here. Okay, so let's not lose sight of the big picture. Okay, so let's do some analysis on this. So if I look at this system here, let's say I want to first solve for IB, right? I want to make sure that this condition is met. Okay, so if I look at IB here, that's this current, the base current. Is this positive? Well, the problem is I don't have any resistor here, so I can't readily apply nodal Ohm's law. So maybe I can go to a KCL. Okay, IE, IB, IC, all right. I can do a KCL, IE equals IB plus IC, or IB equals IE minus IC. It's the same thing, good. I also know from this current controlled current source that IC is equal to beta IB. This is good. I have one equation, but two unknowns. Okay, so how could I solve for IE? Well, here's where our Et250 analysis comes in handy. Look at this. IE is 5, so the node voltage here is 5, minus what's the node voltage here? Going down this way is a little hard to see, but going that way, it's pretty easy. The node voltage there is actually 0.7. So IE is 5 minus 0.7 over R1. So that's written here. Okay, so this is great. I have IE here. I have IB. Look at this. I can solve for IB, right? I bring it over and I move the denominator underneath, right? So let me do that slowly. So IB plus beta IB equals IE, right? And so 1 plus beta IB is equal to IE. And then I move this over, I get that, right? Okay, so then I take this, plug it in. I know what R1 is, and I get that IE is 0.0043 amps, which means IB is 0.000043 amps, and it's positive. So the first condition is met. Yay. Okay, what about the next one? I can do a simple KVL. I need to check VCE. Minus a -15. That's a tricky one. Minus a -15, minus V2, plus VCE, plus V1, plus 5 equals 0. Okay. Could I also do this? I guess I could do this one too, right? I could have gone down this route as well, right? So instead of going V1, 5, I could have gone just straight to 0.7. Either way would have given me a closed loop. Okay, I'm looking for VCE and I want to find V1 and V2. Well, what is V1? What is V2? Well, V1 and V2 can be solved by Ohm's law. Easy, right? So VCE, if I just reduce it down, I just bring everything to the other side, the -15, the V2, the 5, and the minus V1. I'm left with this, minus 20 V1, V2. Well, I know what IE is already done, so the V1 is easy, that's 4.3. But the IC, that's easy too, because it's just beta IB. It's just 100 times this number, okay? And that's times R2. So that's 4.3 volts. I plug these guys in here, and I get minus 11.14 volts for VCE, okay? What does that mean? I've satisfied this condition because this number is less than that. Excellent. So I guessed correctly. So my initial engineering intuition was correct. Good. And then I can't lose sight of the big picture. I'm being asked what is I and what is this V here, that V. Well, by KCL, I'll even write it again. By KCL, I know that I equals IC, and this is our forward active equations. This current here is going to be 0.0043 amps. Nice. So I just, and we've already solved for that, but we're now highlighting it. And what is this V here? Okay, so this V can be solved by this KVL. Now be very careful here. Notice this V is not the 0.7. It'd be tempting to think, oh, you put that positive here, it's oh, it's 0.7, done. No, that V is actually the voltage across both of these. You have VC and the 0.7, right? So if I do a KVL, I got minus V plus VCE plus 0.7 equals 0. So you really have to be careful about all your polarities and where you're assigning everything, okay? So, well, that's not too bad because then it's just the addition of these two. And I already found what VC is, negative 11.4. So it's negative 10.7 volts. Super straightforward. Okay, so we've solved the question. V, this voltage is negative 10.7 and this I is 4.3 milliamps. So keep that in your head, negative 10.7 here and 4.3, because we're going to go to the simulation and see if we got the same thing. Okay, so go back to screen 2 here, and I can now run this, and I put all the values, 1K, 1K. I put a 5 volt here, and I put in a negative 15 there, good. And notice I get negative 10.67, good, that's our V. And I'm getting 4.3 milliamps for IC, okay? This is VCE, that's a negative 11.3, which is matching very closely to our negative 11.4, okay? And we have our base current here, very small, 43 microamps. And these all match the numbers in our analysis. Last thing we can check is this in fact forward active? And if I look down here, I hover over, and sure enough, this is in forward active. Okay, so the link to this simulation is always, as always, in the description, so you can play with it, check it out, and yeah, that's it. I hope this lecture helped, and you learned a little something about large signal DC analysis for a PNP transistor. All right, see you in the next one.